All right, we're going to look at the biogenous sediments now. We'll start with just what are biogenous sediments, and then look at the carbonates, which on this map are in yellow. And then we'll look at the siliceous sediments, which on this map are kind of that dark teal. Biogenous sediments, just like the name implies, are generated by biological activity. And they're a handy-dandy record of fossils over time, so a fossil record. These are described or called oozes, O-O-Z-E. Ooze means it's kind of like a mud. It's gooey. And they are the microscopic hard parts of different animals and plants. Most of them are plankton. Here's plankton. They're free-floating organisms in the ocean. Some of them are benthic organisms that live on the seafloor. The siliceous oozes are going to be either phytoplankton or zooplankton. Phyto are plants, zoo are animals. The phytoplankton and siliceous oozes are diatoms, and the zooplankton are radiolaria. Calcareous oozes similarly have phytoplankton. These are plants, the coccoliths, and zooplankton, which are mostly pteropods or snails. There are some amoeba-like animals that are called forams or foraminifera. The organisms die and fall to the seafloor, and they accumulate there in layers. What can we learn from these biogenous sediments? So again, they're fossils. They're a record of the history of the ocean and the biological activity. They also are going to live at different temperatures. So if we find these fossils, we can use it as a proxy to state the paleo temperature, the temperature of that environment. So I mentioned this earlier, is that they evolve over time. They're not just a stagnant species. So as they're changing over time, we can look at that fossil record and cores of sediments of the seafloor and see the evolution of the organisms. Their hard parts, these tests, are made out of ions that are extracted from seawater. So the chemistry of their hard parts is reflective of the chemistry of the seawater. We can look at them to figure out the chemistry of the ocean from the past. They also can live at specific depths, especially if they're benthic. And then we can tell the paleobathymetry, the paleo depth of the ocean from the fossil evidence. Okay, the first ones are the calcareous ones. These have hard parts that are, turn this back on. These have hard parts that are made out of calcium carbonate. Calcium is Ca, carbon is C, and O is oxygen. That makes up the calcium carbonate molecule. And these accumulate over much of the ocean floor. So look at the map everywhere where it's yellow. In other places, they are also accumulating, but maybe in not as high a quantity. The plants, again, are the coccoliths. They're little single-celled algae, and the forams are little sand-sized single-celled animals. The carbonates are not found in the deepest part of the ocean. The reason is that calcium carbonate dissolves at depths greater than 4,500 meters. In these locations of the ocean, then red clay is going to dominate. I'm going to go back, nope, that way, to the map. So here on the map, notice in these areas that are dominated by yellow, there's patches of red. Those patches of red represent the areas that are deeper than 4,500 meters where the dead carbonate-based organisms and phytoplankton are going to dissolve. They dissolve, and then the clay will dominate, or maybe even the silica oozes could dominate, the siliceous oozes. The White Cliffs of Dover, between England and France, they are made out of coccoliths. Millions and trillions of tiny little microfossils make up those cliffs. There's a video here you can check out about the White Cliffs of Dover, but it's all these little organisms. Okay, the siliceous oozes. So on this map, the siliceous oozes are this dark teal color. They are going to dominate in deep parts of the ocean. They are also phytoplankton and zooplankton. The phytoplankton are called diatoms. Those are algae, and the radiolarians are the single-celled animals. These organisms can be really beautiful, so people make kind of art out of them. I'll show you that in a second. Silica is a glass, so they're single-cell fossils made out of opal or silica or natural glass. Here are some of the plants of the diatoms. Really beautiful. They make up 35% of the global biomass. So these are oxygen producers, and they are produce oxygen in the ocean. They're abundant in areas of high nutrients. One of those is the area around Antarctica. So here's some of the art that is created out of the siliceous organisms. Radiolarian are siliceous or animals. So these are all animals that are single cell and float around as plankton in the ocean. Cosmogenic sediment is sediment from outer space. NASA has a program where they are looking off the coast of Oregon for meteorites, and those are cosmogenic sediments. They're definitely the least abundant sediment on the seafloor. They are mixed in with other sediment, so they're hard to find. You'd have to, in this case, they're sieving out muds, and what would be left behind is the meteorites. Here's the map again of the marine sediments. Cosmogenic sediments, there's not enough of them to even have a color on the map. They're dispersed about all of the ocean basins, but they're really hard to find, and there's not very many of them. So look again at the carbonates. That's the yellow. They're found throughout the ocean basins. The siliceous oozes are found in places where there's high nutrients. So right around Antarctica, those cold waters are very nutrient rich. This is a map of the sea floor of our ocean basins showing the thickness of sediment. The thickness is in meters. So the, let's see here, the lightest blue, where my arrow is here, that is areas where the sediment is not very thick. Here also along the Mid-Atlantic Ridge. So these are ridge areas. The thickest sediment is on the edges of our ocean basins. So over here by the east coast of North America. And also remember these are triginous sediments coming out of the erosion off the Himalayan mountains. So the thickest are near the edges, and the thinnest sediment is near the mid-ocean ridges. So like, for example, this light blue over here, those are basalts that are forming today.